So, hello everyone. Welcome to the first talk of this edition of Motives and Whatnot. Here we have Sabrina Pauli from the University of Oslo talking about quadratic dynamic and excess intersection.
Thank you very much, and thank you very much, Dennis and Maria, for inviting me and organizing all of this, those wonderful conferences. So let me start. So I want to talk about a quadratic version of dynamic at excess intersection. So let me first briefly recall how this is done classically. So if we have X a smooth K variety, then intersection theory is actually happening in the Chow ring, where the nth Chow group can be defined as follows. We take co-dimension endpoints. Those generate this group, and then we mod out by rational equivalence. But let me give you an alternative definition of this, which is due to a formula by alternative definition, which is due to a formula by Bloch and Kato. You can define this nth Chow group as the cohomology of X in the Milnor K-theory sheaf. I don't want to go into details what this is, but this is the motivation for the following definition. So let me define the oriented Chow ring. Okay, as follows. The nth oriented Chow group, here I twist by L is the line bundle over X, is the nth cohomology valued in the now Milnor-Witt K-theory sheaf, twisted by L. Again, I don't want to go into details of this construction of this sheaf, but it contains information of this Milnor sheaf and additional information. This is this Witt here. So it also contains information about the Witt theory. But today, this is supposed to be like a more geometric talk. So what I rather want than this abstract definition is something like this definition. So let's see what this actually is. This cohomology can be computed as a cohomology of the following complex. So we start just like before with codimension 0 points on X, and then we take the direct sum over those of the Milnor-Witt K-theory of the residue field of X, twisted by L. Then we go on and go on, but what we're really interested in, because we're looking at the nth cohomology, is the nth step. And the nth step is generated by codimension endpoints, K0 Milnor-Witt. So along all of those steps here, we decrease this n by 1 until we get to 0, and we increase this by 1 until we get to n of K of X again. And now twisted by L tensor, we have to add something here, namely that -1 mx over mx squared. This is the maximal ideal defining X. And then it even continues. So I want to try to explain a little bit more what this here is. So I don't need to define the whole sheaf. I just need to define what K0 Milnor-Witt is evaluated as at a field. And this has quite a nice, easy description. So if I take F a field, you should have in mind this residue field, f is equal to k of x. Then k0 min of it of f is isomorphic to the Grothendieck grid pairing of f. And you probably all know what this is, but let me give you the definition. This is the group completion of the following, namely of the semi-ring of isometry classes of non-degenerate symmetric bilinear forms. Forms over f. Or if the characteristic of f is not equal to 2, this is just quadratic forms, and that's where the title of my talk comes from. So those are quadratic forms, where the group completion of isometry classes of them. But since every quadratic form can be diagonalized, I can also give you a definition of this in case of generators. So this is generated by rank 1 quadratic forms, or symmetric bilinear form, which I denote by bracket u bracket, which is the class of the following form. Here's the symmetric bilinear form, which sends x comma y to u xy. And of course, u here has to be, has to be a unit, otherwise this would not be non-degenerate. But if I replace x by some vx and y by some vy, this is isometric to this, so, and I get the form uv squared, but they are the same, so I can divide out by unit squared here. So this is subject to the following relations. The first I already mentioned, u is the same as uv squared. uv is the same as u times v. And adding is a little more complicated. U plus v is the same as uv plus uv times u plus v. And let me add a fourth relation, which is actually not necessary, but it simplifies calculations a lot. So the last relation I want to give is u plus minus u is equal to 1 plus minus 1. And since this is such a special form, I want to give it a name. I denote it by an h and call it hyperbolic form. So I said I wanted a description like for the classical Chow ring for the oriented Chow. I don't quite get this, but I can at least tell you what the elements in there are. So let me put this in quotation marks. So the elements in this oriented Chow are symmetric bilinear forms or quadratic forms when the characteristic is not 2, over k of x for x in codimension n, twisted by some line bundle. Let me try to explain what this twisted by some line bundle means. Well, we have seen that from f star, we get to map into k star min of it of f, sending u to this rank 1 form. So now I can at least define k min of it f comma l to be the tensor product k min of it f tensored C joint units in f, C adjoint units in L, where L is a one-dimensional F vector space. So instead of just remembering a quadratic form, we also remember some non-zero element of some fiber of a line bundle, which will usually be some, this will usually be, whoopsie, I'm sorry. This will usually be some orientation bundle, so we have to remember some orientation. That's why it's called oriented Chow. Okay, let me tell you some properties of this. So first of all, I already told you this Milnovich K-Field sheaf contains information of the Milnor K-Field sheaf. So there's a map from here into the Milnor K-Field sheaf, which induces a map from oriented Chow to Chow. So we can recover classical results from oriented Chow. And now some functuality properties. If I have a map from Y to X and a line bundle on X, there is a pullback from Chow n X comma L to Chow n Y comma, and now we need the line bundle on Y. Well, the natural choice is the pullback of L. And for f from Y to X proper, we even get a push forward, but this is a little more complicated. And now you see why we really need this twist here, because otherwise we couldn't define this. So the push forward goes from show n y f upper star L, but now we have to tensor with omega y over k. So this is the determinant of the sheaf of differentials on k differentials on y to Chow. So let D be dimension x minus dimension y. Then we have n plus d x L tensor omega xk. Okay. So this is all the properties I wanted to mention. Now I want to compute some examples of this, but let me first define an Euler class and an Euler number, and then I will compute some Euler classes and Euler numbers. So let V to Y be a vector bundle, and let the rank of this vector bundle be R, and let this S0 here be the zero section. What I can do, I can start in oriented Chow 0 of Y, and I don't twist by anything, or just twist by the trivial line bundle, so I don't put anything in here, and I claim that there is a 1 in here, which is really just this form 1, because if we go back to this complex, which computes this here, well, if I assume, let's assume that Y is irreducible, so we don't have a direct sum in here, then we really have something in here. We don't have any twist, so we can forget about this L. So this is K0 of K of Y. And there's a 1 in here. And this is actually in the kernel, so this is of this complex, so this is an element of this oriented Chow 0 of Y. And then I can push forward by the zero section, and I land in oriented Chow R, V, and now I need a twist. And I claim that I can twist by pi upper star of the inverse of the determinant of the vector bundle V. Why is that? Well, this here, pi upper star, det minus 1 of V, is isomorphic to omega Vk tensor pi upper star omega Yk minus 1. So this is pretty much what we want. If we look at this pullback here, we have this omega V over K tensor something. So now we want the pullback of this something to be in here. So let's see what this pullback is. So S0 upper star pi upper star omega yk minus 1. Well, what is this? This is actually just omega yk minus 1. And this is very convenient because I could just twist by omega yk tensor omega yk minus 1. And now I can pull back by the 0 section, and I land in oriented Chow R v det minus 1 v for a similar reason. So if I pull back this here by the 0 section, I get, for the same reason, I get this. So this works. And I call the image of the 1 in here, I denote it by E of v, and I call it the Euler class. Okay. And in very nice situations, I can take the degree of this Euler class and I get a quadratic form, not the twisted one, but I get just the quadratic form, and this I call the Euler number. So let me elaborate on this. Now assume that the rank of our vector bundle, I call it R, is equal to the dimension of Y. And let's also assume that the structure map from Y to spec K is proper. So I can apply push forward. And let's also assume that V is relatively oriented. And by this I mean that there's an isomorphism, let's call it rho, from omega yk tensor the determinant bundle of V to the square of a line bundle. And now L is a line bundle over Y. So why do we need this? Well, let's see. This Euler class lived in oriented Chow R V twisted by det minus 1 of V. Now, this is an isomorphism. Now this isomorphism identifies this oriented Chow group with oriented Chow R V, Y, sorry, Y. With twisted in L tensor minus 2 tensor this canonical sheaf. And I've already used many times that quadratic forms really don't care about squares, so I can also cross out this one. And now I can apply, now we're in a really good situation to apply this push forward map, this one here, because we already twisted by this guy here. And then where we land this in is Chow 0 of spec K, twisted, well, by omega K over K, which is just nothing. And this is just the growth in the grid thing of K. And I call the image of this Euler class in here, I denote it by NV comma rho, because it depends on this relative orientation, and I call it Euler number.
Sabrina?
Yes.
I'll ask a question. So in general, rho may not, I mean, this isomorphism may not exist, right?
Yeah, it may not exist. Thank you, I should have pointed this out. Good comment. We will also see an example later where this not necessarily exists. Okay, let me give you an example. If I just take V to be the tangent bundle of Y, then the Euler class lives in oriented Chow R Y determinant inverse of the tangent bundle. But what is this? This is the determinant of the cotangent bundle, well, but this is exactly what we want. So this is very naturally oriented or relatively oriented. And the image of P lower star in Grothendieck width is also denoted by psi of y, and called the Euler characteristic. And if you want to learn more about this and see some examples, there's a paper by Mark Levine who defines this. Okay, but now let's start with the computation. I said I wanted to compute some of those Euler numbers. So let me give you a formula. The first thing I want to tell you is follows from, or was developed by Jesse Kass and Kirsten Wickelgren. Who found the formulas for this Euler numbers. So let me recall the setting. We have a vector bundle over y, and the rank of this vector bundle was r, which was equal to the dimension of y. And we had that, let's assume that y is smooth and proper. And that there is a relative orientation. Like this. Now let's take a section of this bundle, not the zero section, but a very general section, and assume that the section, the zero locus of the section, let's call it Z, is just the union of finitely many closed points. So there's a closed points. And let's also assume that all of those residue fields are separable over K. Oops. Then Jesse Kass and Kirsten Wickelgren show that this Euler number is equal to the sum over those x's of local contributions, which I call local index. So let me tell you what this local index is. Well, the picture is locally around, those points are isolated. Locally, we take a local neighborhood, we collapse the boundary, we get the map of spheres, and it's something like the local degree. But there's even an explicit formula for those. So what you need to do is we need to choose coordinates. Those are called Misnevich coordinates around those points. So here, this is a point in here around X. This is just an Étale map from U, which is the neighborhood of X, to AR. Étale means we have an isomorphism on the tangent space. So we actually have coordinates on X. And this psi should induce an isomorphism on the residue field. And let's choose a trivialization of our vector bundle. And this should be compatible, both those coordinates and this trivialization, with our relative orientation. Let me just say in words what this means. Well, those coordinates here give you a distinguished generator of this line bundle, and this trivialization gives you a distinguished generator of this line bundle, and we want to that those two, the tensor product of those two is a square in here. Because if I choose different coordinates, then I also have to choose a different trivialization, and what I get is something which differs by a square from what we had before. And this makes it well defined in Grothendieck-Witt, because Grothendieck-Witt doesn't really care about squares. So this is what I mean by that. And then in those coordinates, locally around x, I can express this section sigma as our polynomials functions from AR to AR. And this local contribution of x to the Euler number is almost the determinant of the Jacobian of those f1 to fr. So determinant dfi d, let's say t, tj, so this here are my coordinates, or the fi are polynomials in the tj. I evaluate at x, and I take the rank 1 form of this. But this might not be in Grothendieck-Witt of k, but Grothendieck-Witt of k of x, so I have to take a transfer. Let me also tell you what this actually is here. I assume that k of x was separable over k, and if I have a form over k of x, so symmetric bilinear form over k of x, let's call it B, then I can compose with the field trace k of x over k to k, and this whole is a form over k, and I call this the trace k of x, k of B. Okay, so this is the formula. You'll later see an example where I actually compute this, so keep this in mind. And as an example, what Jesse Kass and Kirsten Wickelgren had in mind when they defined this was to compute a count of lines on a cubic surface valued in Grothendieck-Witt of k. And this can be computed as the Euler number of sim 3 as dual. This is the tautological bundle on the Grassmannian of lines in P3. Also, this might become clearer later in the example of quintic threefolds. This has a kind of canonical relative orientation, so I don't put the row in here. And they compute this to be 15 times 1 plus 12 times minus 1 in Grothendieck-Witt of k. Well, earlier I said I can get the result in the classical Chow ring from this. And you can see very nicely that this is actually the case. Namely, if I take the rank of this, I get 27. And this is the classical line count on a smooth cubic surface. Okay.
So, sorry, this is perhaps a naive question, but is there, I mean, if you take the rank, you get literally the number of lines, saving this in some sense. Is there a way of thinking of these Grothendieck classes as counting something?
Yeah, we kind of, okay, so I don't know if this answers your question, but
suppose we take the signature, suppose we are over R or whatever. Do we
yeah, exactly. So if I take the signature, I get the real result. So this Grothendieck-Witt over K gives you, first of all, information for whichever field you're in, and you can get much information out of this, like getting the real and the complex count.
Oh, so for example, over a real cubic, you'd expect that to be like 3 lines?
Almost. Over the real cubic, you can get three lines. You always get at least 3 lines. But what you actually have is, if you look at, I said that the Grothendieck-Witt of R is generated by elements U in units in R, units of R squared, but this is just plus or minus 1. So what you get is a sign count. To each of those lines, for example, on the cubic surface, you assign either a plus or minus 1, and if you sum up those signs, you get 3. but it can happen that all 27 complex lines are actually real, or it can happen that they're just 3 lines.
I see. Thank you.
Thanks for the question. I think that illustrated well what is happening. Okay. So, but my title of the talk was actually what happens in a excess situation. So this sigma I just gave, this just works for very, very specific sections sigma, sigma, where this is finitely many closed points. And I also assumed that this here is actually not 0, because if this here were 0, then this wouldn't give you a non-degenerate quadratic form. So first question, what if this determinant dfi dtj applied to x is 0? Well, the answer to this is we can compute this local contribution with the EKL form. This stands for first Eisenbach and Levine, but this is Harold Levine, not Mark Levine, and Kim Chiavilli, who did define something like a local Brouwer degree, or gave an algebraic formula for the local Brouwer degree in this case over R. And then Kuss and Wickelgren showed, well, this also works over any field K, so I want to refer to their work if you're interested in this case. And there's a paper by a bunch of people extending this result. So this case is covered, but what about an excess intersection? So what do I mean by this? What if I choose a section sigma is equal to 0, equal to z, such that z has a positive dimensional component? As I already said, this is classically an excess intersection problem. So we want something like an excess intersection formula for oriented Chow. And this has been done. So there's an excess intersection formula for oriented Chow, which was first proven by Fazel. And then there's a paper by Diglis, Jin, Khan, extending those results. And the formula for the Euler number I'm writing down now is you can find in a paper by Tom Bachmann and Kirsten Wickelgren. Namely the following: if I assume that z in y is regularly embedded, then this Euler number nv comma rho is equal to the sum over, I take closed and open components in z, and it's the sum over the Euler numbers of something called the excess bundle of this excess intersection. And this relative orientation rho here gives me a relative orientation of this bundle, this excess bundle. So let me tell you what this excess bundle is. So E is the co-kernel of, so the normal cone of Z and Y sits in the restriction of the vector bundle to Z. And the co-kernel of this is a vector bundle on Z of the correct rank, and it's relatively orientable. So I can express this Euler number in terms of this maybe easier Euler number here. So I think I've done a lot of theory now. So it's time for a change, and I want to do a really nice example where I give an example of this axis bundle and account and actually compute something in quadratic forms. And because of time issues, I prepared this. Here we go. So I was looking for an example of axis intersection, and that's what you do when you want applications. You go to the 3264 book and look what they do. And one of the first examples there is the following. You take three surfaces in P3. So they are hypersurfaces defined by some polynomial of degree small s1, s2, and s3 respectively. And let's assume that, well, usually, like if you intersect them, you would expect a zero-dimensional intersection. But let's assume this is an axis intersection, and like also a very nice, easy axis intersection, namely that they intersect in a line and something zero-dimensional. Let's assume those two are disjoint, so everything works out nicely. And the question in the book they ask is, what is the degree of this gamma? So how many points are actually in there? So I want to ask a new question, namely, what is the oriented degree of this gamma? So what I mean by this, what is the sum of those local contributions in here? So intersecting three hypersurfaces in P3, this is, we know classically is the Bizu Theorem. And the Bizu Theorem is actually, you can translate it, and computing the Bizu is just computing the Euler number, oops, I'm sorry. Is computing the Euler number of this bundle. Because those three surfaces define section of this bundle. And the Euler number of this bundle is the classical Bizu theorem. But now I want this bundle to be relatively oriented, so I can compute the Euler number of it. So let's do this. So we want that this here is the square of a line bundle. So let's compute this. So omega P3 is O of -4. And the determinant of our vector bundle, well, this is an O of S1 plus S2 plus S3. So this is O of S1 plus S2 plus S3 minus 4. And we want this to be a square, so we want this guy in here to be even. So this is relatively orientable, or a square of a line bundle if and only if S1 plus S2 plus S3 is even. Okay. And then in this case, the Euler number of this vector bundle is equal to S1 times S2 times S3, which would be classically the result of Bizu. But now I have to divide by 2 times a hyperbolic form. So 1 plus minus 1. And I also denoted this by H earlier. This you can, for example, look up in Stephen McKean's paper, who wrote a paper about an arithmetic version of the Bizu theorem, where he finds a Bizu theorem valued in Grothendieck-Witt of K, and he also gives geometric interpretation of those local contributions of those intersections. Okay, now let's go back to this axis intersection formula for Euler numbers. So the Euler number of this bundle here, of V, is equal to the sum of Euler numbers of the closed and open components of this intersection. So this was, first of all, the Euler number of this axis bundle restricted to our line L, plus, well, the Euler numbers of these axis bundles on the point, but this is just the local indices. And I want to compute this. I have already computed this, so let's figure out what this here is. Okay, so
Sorry,
yes.
could you please show again? So why could you compute n of v, although there were non-zero dimensional components?
Well, this order number is actually, okay, thank you. This order number is actually independent of the section you choose. So what you could do is, for example, you could choose a better section. You could choose better surfaces which actually intersect in something finite dimensional, and then you can sum up the local contributions. And it really doesn't matter which sections you choose. And then where is this? In this paper, Stephen shows that you will always get the classical count over 2 times the hyperbolic form. In this case, this is also quite easy because this vector bundle has odd rank, and odd rank vector bundles will always have an Euler number as a multiple of this hyperbolic form, and we know the rank should be the classical count. So this is
I
what
see,
it should
thank
be.
you.
So this doesn't depend on the section. Yeah, I should have said, thank you. But I could also express it as this sum here. Okay, so I was about to compute this Euler number here. So I said this axis bundle was the co-kernel of the normal bundle of L and P3 inside this vector bundle V restricted to L. So I can compute the determinant of this normal bundle of L in P3 in the following way. Well, I have an exact sequence from the tangent bundle of L to tangent bundle of P3 restricted to L to the normal bundle of L and P3. I know the determinant of TL is an O of 2, and the determinant of TP3 restricted to L is an O of 4. So the determinant of this normal bundle is an O of 2 over P1, because the line is just in P1. And the determinant of V restricted to L, well, this is an O of S1 plus S2 plus S3. So this axis bundle is equal to its determinant because it's a line bundle if you count the ranks, and really should be. Then and you can see that it's O of P1 of this here, S1 plus S2 plus S3 minus 2. And now we can take Stephen McKean's paper again to see what this Euler number should be, because this is again a case of the Bizu theorem. Well, it's S1 plus S2 plus S3 minus 2 over 2. So the sum of those local contributions is equal to S1.
Do you need that times H?
Oh, thank you very much. Yes. Is S1 times S2 times S3 minus S1 minus S2 minus S3 plus 2 divided by 2 times H. And now what we can do is we can go back to the book, the 3264 book, and compare it with the result in there, and then we can see that the degree of gamma is indeed S1, S2, S3 minus S1 minus S2 minus S3 plus 2. So this seems to be correct. Okay, but now I want to give you a more geometric picture of what is happening here. So I prepared something, namely a picture. So let sigma be the section defined by, so let this be F1, F2, F3, where our surfaces were just the zero locus of the vanishing locus of the Fi. Then we knew that there was an axis intersection. Now what I can do is, there's a dynamic interpretation of this axis intersection. I can take this section and deform it. like this. So I add t times some other section plus t squared times some other section, and so on and so forth. And what is happening then? Well, if I take the fiber over 0, that's what I drew here. I get this line L, which I drew in green here, and gamma I drew to be 2 points. But in general, when t is not equal to 0, the fiber over t will look differently. You will only have a finite intersection because that's what you're supposed to have. So what is happening is, let me choose a different color. Those points will deform over t to other points. But then there will be finitely many points on L which will deform too. And we need like an even number we've just seen, so let me just take 2. So there will be a point here, and let's say here, which deforms. Like this. And classically what happens is now, if I highlight those 2 points, then so the highlighted points define a 0 cycle on L, so it's in show 1 of L, so this is a 0 cycle, and let me call it alpha, and the degree of this alpha will be this Euler number of the axis bundle. And if I take a different deformation, of course these 2 points will change, but the other cycle alpha prime will be rationally equivalent to the first alpha. So this gives a different way to compute this let's say Euler number using a deformation. So let me go back to the talk and do this in an oriented version, an oriented Chow. Okay, so quadratic dynamic intersection. And I'm just doing this now for Euler numbers. So I had this section, sorry, this deformed section, which was, I have a section where the 0 locus is possibly an axis, and I add t times another section, t squared times another section, and so on and so forth. So now I get like a new section, and I want to view this section as a section of the base changed vector bundle. So now I just base change to the field of Laurent series in T. And then I get an Euler number of this base change bundle in Grothendieck width of KT. And the nice thing about Euler classes and Euler numbers, or one nice thing about them, is that they commute this with this base change. So what do I mean by this? I can include the Grothendieck width of K in the Grothendieck width of KT by just sending a rank 1 form U to U, but now over the bigger field. And this map here is injective. And what happens is that if I take the Euler number over K, so the not base changed one, this is mapped to the Euler number of the base changed bundle. And since this map is injective, I can recover this Euler number from this Euler number. And here I have expressed it as a sum of local indices, which are easy to compute. We don't need an excess bundle, which might be complicated. And this sounds like a really, really easy idea, but I realize this is quite powerful. It is actually often easier to compute local indices at deformations, even though it sounds complicated. So let me give you the example where I used this. Okay, perfect. As I announced in my abstract, I want to compute the count of lines on the Fermat quintic threefold. So let's start with some definitions. By GR25, what I mean is the Grassmannian of two planes in 5 space, or equivalently lines in P4. And over this Grassmannian, I claim I have a vector bundle, and this vector bundle I denote by sim5 as dual, and I want to tell you what the fiber over point is. So let L be a 2-plane or a line in P4, then I denote the point defined by L, I put some brackets around it. So this is a point in the Grassmannian. And the fiber over this point should be degree 5 polynomials on the line. And then I claim that the Euler number of this vector bundle, first of all, it's defined. So the rank of this vector bundle is 6, the dimension of this Grassmannian is 6, so the rank and dimensions works, and there's also a canonical choice of a relative orientation. So there is an Euler number, and it counts lines on a quintic threefold. Let me explain to you why. So if I take a quintic threefold X, that means it's a hypersurface in P4, defined by the vanishing of a polynomial of degree 5. Then I claim that this quintic threefold actually defines a section of this vector bundle, namely as follows. Again, let this L here be a line in P4, and I put the brackets around to say this is the point in the Grassmannian, and the image of this point in the vector bundle should be a degree 5 polynomial on the line, and I define it to be f restricted to L. So f was of degree 5 here in P4, I restrict it to a subspace. Yeah, that's how it works. And then you can see that while sigma f of L is equal to 0, if and only if f restricted to L is equal to 0, but this is exactly when L is on our threefold. So this is why this Euler number here actually counts lines on the quintic threefold. Okay, and now I wanted to compute this and find a really nice quintic threefold where I know all the lines, and I compute these local contributions, but I kind of failed doing this. It was really complicated. It doesn't sound so complicated, but the nicest quintic threefold I could find was the so-called Fermat quintic threefold, defined by this Fermat equation here. So x0 to the 5 plus x1 to the 5 plus x2 to the 5 plus x3 to the 5 plus x4 to the 5 is equal to 0. And here I actually know all the lines on there, but there's one problem. This zero scheme here, defined by this section, defined by the Fermat, so I guess this should be the big F, capital F, is one-dimensional, so it's not zero-dimensional. So I again have this axis intersection situation. And I also can explain to you why. Here is how the lines on X actually look like. So if I take U and V to be the coordinates on the line, so L is a 2-plane, so there's 2 coordinates, then all the lines on our Fermat look like this. We have U minus zeta u. Zeta is a fifth root of unity. And then AV, BV, CV, such that, well, now we can plug this into this equation here. So u to the 5 plus minus zeta u to the 5 is 0. And then we want AV to the 5 plus BV to the 5 plus CV to the 5 to be 0 too. So we have the restriction that A to the 5 plus B to the 5 plus C to the 5 is 0. But for any choice of A, B, and C, such that A to the 5 plus B to the 5 plus C to the 5 is 0, we get a line on our Fermat quintic threefold. So our zero scheme is the union of many degree 5 curves. And I tell you that it's 50 because, well, I could choose those two. I could just do permutation of coordinates and put them somewhere else, and then 50 is equal to 5, choose 2 times 5, because I have 5 different choices for my zeta here. So my zero scheme is the union of 50 degree 1 curves. And this has been found by Albano and Katz, who did this over the complex numbers. And they also looked at deformations of this Fermat quintic threefold. And what they found is that on each of those components C, there are 10 lines and that deform with multiplicity 2. I'll show you in a picture later what this means. And then they also looked at lines which line in the intersection of 2 components. There are finitely many of those, and those all deform with multiplicity 5. And then there's a paper by Clements and Clay, again over the complex numbers, who look at this zero scheme Z and look how it looks locally. And they find it looks like, I guess we want to see here, CXY, x to the 3, y squared, x squared, y to the 3. So if I do this deformation picture again at 0, what I get is something like a thick cross. So the zero locus of this here is something like a thickened cross. Wow, not so nice, but this is the cross. This is what the zero locus looks like. And let's take one of the points, one of those here, which deform with multiplicity 2. By this I mean, if this one, let's assume this deforms, then there are 2 points that go into here. And I said at the intersection, that would be here. This deforms with multiplicity 5. So there's 5 points in the Riemannian approaching this. Like this. So this is the picture. And I did all those computations again, and I pretty much saw that this all works over any field, assuming that the characteristic is not equal to 2 or 5. So let's assume that the characteristic of K is not equal to 2 or 5. And I want to now concentrate on this intersection point, and I want to compute the local contribution of this one to the Euler number. And I can take the following deformation of my Fermat quintic threefold. I take F, this is the Fermat equation, and I add T to the 5. That's because it deforms with multiplicity 5, and it makes the computations easier. And the easiest G I can choose such that this point deforms is, let's say, minus A x0 to the 3 x2 squared minus B x0 squared x2 to the 3. You can also choose different ones. I chose this one because it's the easiest for my computations. Then I said this point, this line in the intersection here deforms. Let me fix this line. This is u minus u, v minus v. 0. So this line obviously lies on the Fermat, and you can also easily see that it lies on this intersection. And I claim that this line deforms with this deformation. So let's look at the zero scheme defined by this deformation here. Then I can also do this local structure, and locally it looks like K, oh, I guess I work over KT now. XY, x to the 3 y squared minus t to the 5a, x squared y to the 3 minus t to the 5b. And then you can see if let me call this ft and this gt. Put a spec in front of this. Okay, now if I choose x to be t times the 5th root of a cubed over b squared and y t times 5th root of b cubed over a squared, if you plug this in into ft and gt, you can see that this is a 0. It's also an isolated 0. So I can compute the local contribution of this point. So let's do this. I want to compute this local contribution. And I said earlier, the formula for this was I take the trace over where it is defined of the determinant of the Jacobian evaluated at this point. So this looks really complicated, but it's not. And where are those points defined? Well, we have to join some 5th root. So it suffices to take e to be kt adjoint the 5th root of a times b. So this is e. And then you can do the computation. You compute the Jacobian and its determinant, and what you get is 5 times t to the 4 times the 5th root of ab squared. But we're in Grothendieck width of e, so we can forget about squares. So this is just a 5. And if you take the trace of this, you get 2 times h plus a 1. So this line contributes 2 times h plus a 1 to our Euler number. Now, I said there could also be 5th root of unity, where it's a little more complicated because they're not necessarily defined over a base field k. So I have to take the trace of 2h plus 1. And this I computed to be, well, the 2h turn into 8h because this is a field of extension of degree 4, plus this 1 turns to 1h plus a 1 plus a minus 5. And then with the similar computation, you can show that all the multiplicity 2 lines compute just an h. So now let me sum up everything to get our Euler number. So of this first type here, if I commute the coordinates, there are 15 different choices, namely 5 choose 2 times 3 choose 2 divided by 2, because I counted twice, this is 15. Of the second type here, let me say there will be 90 of those. And I said there are 50 components, and on each there are 10 lines which contribute an h. So this is 50 times 10. So now if the characteristic of my field is not equal to 5, which I assumed, I can actually replace this guy here with an h. It doesn't change the result in the end. So what I get is 30, so this is 15 times 2 plus 90 times 10 plus 500 times an h plus 15 times 1. So this is 1 for 30 times h plus 15 times 1. And again, if I take the rank, this is 2,875, which is the classical count. And now let's also take the signature, and I get 15, and this is the real count. So this seemed to have worked. Yeah, I think, oh, my time is up, was up 4 minutes ago, and I want to finish here. Thank you very much.
Thank you for this beautiful talk. Does anyone have questions?
Well, I have a question. I'm not sure how much sense this makes. But so let's say you have some smooth variety and a vector bundle, and you take a section and you look at the vanishing locus. And let's say the vector bundle has rank equal to the dimension of the smooth thing. And then let's say the vanishing locus is, you have some component, not zero dimensional, and then bunch of points. So this is like the example before, but more general.
Yeah.
So let's also assume that maybe the large dimensional component is not regularly embedded, so you cannot use any kind of excess intersection formula.
Yeah.
Well, you could still compute what should be the class of that one in Chow groups or in Chow rings using its virtual fundamental class. Because,
yeah.
So my question is there something similar in these oriented Chow groups? Can you compute this?
I'm not the expert on this, but there's a paper by Mark Levine who defines virtual fundamental classes, but I please don't ask me about this. I don't know.
Okay.
But
yeah,
I think
it's probably
there is
the right
something
thing then if it's by Mark.
Yeah.
Thanks.
I have a naive question. So could you maybe explain again shortly the main idea of this dynamic approach? So as far as I understand, you have this like good situation when your z is just several points, and then bad situation when z is positive dimensional, and you can somehow so if you can consider a family where you're like good, 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 bad, good, 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 right? And the so then how do you, like, what's the main idea of the method? How do you compute?
Okay, so
can you take some kind of limit or something like that?
Okay, yeah, okay. I guess you can. So what I've done now is very naively. I just compute here in the Grothendieck width of KT, and I know what I get is in the image of this I, and then I can, since this I is injective, I can just get it. But what you actually want is something like a limit cycle. I bet there is one. So I guess what you could do is, so if you have your z, and this is positive dimensional. So this is my zero locus. So what I could do now is, well, I can take this ct, which is my deformed section, is equal to 0. Then I can take the tensor product, or the fiber product over, I take out the 0 locus. So in the picture is, I have something bad here, something finite dimensional here, and I take out this bad part in the middle. And let me call this Z star. And then I could take the closure. That's what Fulton does. Let's take the closure of Z star in Z. And then Fulton defines the limit cycle to be kind of the cycle defined by the fiber. So you can take the fiber over 0 in here. Well, this is exactly what we want. That's those 2 points here, which is purple. I hope you can see it. Now they're green. So this closure is just those pink lines, and this this fiber over 0 is just those 2 points. And Fulton defines the limit cycle to be the cycle defined by this. So now this is a little more complicated in oriented Chow, because we don't have this really nice mod rational equivalence definition. But I guess what you can do is Fasel defines something like a map from oriented Chow of Z prime to oriented Chow of this limit cycle. And I think he denoted by mu t. So this is something like a pullback along a divisor. And I hope, and I bet with you, that the image of the 0 cycles in here gives you the correct result in here. But I haven't worked this out yet. But thank you.
Yeah, cool. Thank you. Yeah, that's what I would try to do if I were doing this. Yeah, you should try it.
Yeah.
Okay, we have a question in chat by Stephen McKean. Are there vector bundles over the formal deformation that don't arise as the base change of a vector bundle? It would be fun if you had an Euler class of vk brackets brackets t that didn't lie in the image of gwk.
I doubt that. Because like this Euler number really commutes with base change, and you could base change up and go back and forth. So I really doubt that. But you can come up with an example, and yeah.
Okay.
That's kind of like split in principle idea, right? Base changing to k of t.
Why is that?
Oh, maybe let's discuss it later. I didn't formulate a precise statement yet. Sorry.
Oh, another question by Tony. If y is singular, then there should be more vector bundles, no? I think he's referring to the previous question.
Yeah, exactly. I think then you should have even more line bundles, but maybe I'm wrong. I don't know.
What do you mean by referring to the previous question?
I mean, I think I think he's saying that if you take the formal deformation of y, like yk brackets brackets t, then it can support vector bundles that are not base changed by y.
Okay.
Which is probably true when y is singular because you don't have a one invariance or something. But then, I'm not sure I follow, actually, because we were asking explicitly of vector bundles vk brackets v brackets brackets t. So I'm not sure. Anyway. Anyway.
Yeah, I don't know what to add.
You should overthink more your ideas.
No questions? Let's thank the speaker again. Stop the recording.